Welcome to the New Quantum Era, the podcast where we talk to researchers in the field of quantum information science and technology. I'm your host, Sebastian Hassinger. We will be talking with Dr. Zoe Holmes today on today's episode. The topic we're going to discuss is her recent work in the area of variational techniques. So these are things like the variational quantum Eigensolver, and they generally are efforts to see if there are ways that we can use these devices we can create today, these noisy intermediate scale quantum devices, in conjunction with classical computing in a hybrid algorithm or a hybrid approach to providing some sort of scientific value, computational value, even before we have fault-tolerant devices. And Zoe's been looking at this for a number of years with collaborators, testing some of the difficulties in getting results from variational techniques and also investigating new approaches to this type of solution, in particular quantum imaginary time evolution, which was the topic of the paper that I read that prompted me to reach out to Zoe and ask her if she would be on the show. She agreed to join us on the podcast, and this conversation is the result, and I think you'll enjoy it. It's quite interesting, so let's take a listen. Welcome back to the podcast. We're joined today by Professor Zoe Holmes from EPFL in Lausanne, Switzerland. She's a professor of physics there. She's been there for a few years. She's got a PhD from Imperial, and she did her undergraduate at Oxford. And she's been doing a lot of interesting work in variational techniques and seeing what the limits are from what we can get out of NISQ machines or algorithms that can run on the systems we have today. So welcome, Zoe. Thank you for joining us.
Cool. Thanks for having me.
Excellent. So I became interested in your work last year sometime. There was a paper on quantum imaginary time evolution that seemed like a novel approach to the kind of variational techniques that quantum VQE and other variational hybrid algorithms that are trying to get the most out of these NISQ machines that are available today. Is that something you're still working on? Is it you're sort of probing what the limits are, what we can expect to get out of these machines?
So that paper that you're talking about is all about going back to sort of the philosophy that nature's actually really good at finding ground states.
Right.
But if we try and force ourselves to find them, if we just search randomly, that seems pretty hard. So nature's good at finding ground states by cooling. So let's try and use a cooling-inspired algorithm to come up with an approach that is guaranteed to converge to the ground state. And this is not an entirely novel idea. People have been playing around with this in different ways for a long time. But we have a new way of doing it and some nice guarantees for it.
And so, but cooling inspired, how does that differ from the standard VQE kind of approach for trying to find ground state?
Okay, so VQE, you have a cost function, a parameterized cost function, and a parameterized guess state. So the cost function tells you the energy of your parameterized guess state. And what you've got to do is you've got to apply an optimization algorithm, try and find the best set of parameters to try and minimize that energy, which will then give you the ground state. But that search can be that optimization problem. So it's a very simple algorithm in theory, but the optimization problem can be very hard. So time and time again, people have seen a number of different problems. So the one that I've looked into most is that in a quantum setting, the landscapes you're trying to optimize, in some sense, become very, very flat. With high probability, if you pick any randomly chosen parameter setting, the gradients you get at that parameter setting, that point in the landscape, will be very, very close to zero. Exponentially close to zero. So the bigger, exponentially in the size of your problem. So the bigger and bigger you make your problem, the system you're looking at, the smaller the probability of actually observing gradients. Big problem for VQE. Another big problem for VQE is local minima. It seems like quantum
The
landscapes are
barren plateau. Yeah.
no. So beyond barren plateaus. So the phenomenon I saw before was barren plateau, where your units get really, really flat. But even beyond the barren plateau phenomenon, it seems like these landscapes are an absolute mess. You have lots of really shallow, bad minima that are a long way away from, which is generally thought to be in contrast to the case classically, where you tend to have your minima collect towards a reasonable solution. So that's a second problem. And then you've also got sort of expressivity concerns, like how the hell do you come up with a guess for this guess state? And there are some ideas in certain contexts. For example, the UCC, unitary coupled cluster ansatz for chemistry. But in other contexts, people just have not many good ideas, or it's not obvious what the right solution is for coming up with a good guess ansatz. So our approach using imaginary time evolution throws all of those problems away. And instead, what you do is you have this well-defined circuit that is guaranteed, if it gets deep enough, to prepare the ground state. Now, there are downsides of that. Your circuit can end up very, very deep. More deep than you're going to be able to do, certainly on current hardware, and maybe not in the next 5 years, but maybe in 10, 15 years. We'll see.
Right. And that guarantee is because the circuit is, as you said, cooling inspired, and cooling is nature's way of finding ground state, and it's infallible.
Exactly.
Yeah, that's really interesting. And so, I guess is there any difference in sort of one of the arguments about VQE, or the criticism of VQE and other variational approaches, is they are heuristics, right? They're not theoretically provable to be efficient. Is that something that the imaginary time evolution approach gets around, or is it also a heuristic?
No, it's not heuristic. It's completely non-heuristic. But because of that, the circuit depths are larger. So we have this guarantee that a single iteration will decrease your energy by an amount proportional to the energy fluctuations in your initial state, for example. So we have a guarantee in how much a certain circuit depth will cool it. But the circuit depth can end up.
Right. And is that circuit depth that's guaranteed to cool it by a certain amount, is that proportional to the size of the system that you're trying to estimate the ground state of?
The circuit depth, is it proportional to the size of the system?
In other words, the larger the quantum system you're trying to simulate, are you anticipating you'll need a deeper circuit to,
Exactly.
Yeah. Interesting. So what would the sort of, in your experience, what would be sort of the minimal practical requirements for depth of circuit you need to support for imaginary time evolution to be useful?
We have not really done those calculations yet, because the thing that makes it harder is so you asked whether our algorithm was heuristic or not. The paper we put out recently was not heuristic. It was really giving these guarantees
Right.
in a certain regime. But actually, I think there are sort of more heuristic versions of it that could, in practice, work out better, but that we don't have guarantees for yet. So what it boils down to is we have to use what we call a short step. We have to do these kind of really short steps to so our circuit with a short imaginary time step will approximate imaginary time evolution. It will approximate cooling. But if we have that time step short, we can guarantee that we're well approximating imaginary time evolution. And if we're well approximating imaginary time evolution, we have guarantees that you're going to converge towards the ground state. However, when you have these short time steps, you need lots and lots of them. We only have guarantees basically in the infinite time limit. So if you have short time steps, you need loads and loads of time steps, and that leads to deep circuits. On the other hand, you may well be able to get away with a much bigger time step. We do have some numerical evidence of that. However, we don't have guarantees then.
I see. So Is it analogous to analogous to if the large time step you're sort of getting two data points that are further apart and sort of extrapolating between those two data points? Is that somewhat
No,
analogous?
it's what we have is we have a number of approximations to get from an algorithm that exactly implements imaginary time evolution, which is guaranteed to converge, to some circuit that approximates imaginary time
Okay.
evolution.
Okay.
How well our circuit approximates imaginary time evolution depends on this step size.
Right. Okay. And so, I mean, that sounds like the category of trade-offs and searching for tricks that is kind of required by the type of device that's available today to run on run circuits on real hardware. Is that sort of the case? You're you're trying to make the best you can out of the noisy machines that are available today.
Yeah, so if we wanted to try and use this approach on current devices, you would either have to accept that you are not getting anywhere near the ground state, but you're just getting a slightly better approximation. Um, so there is actually another paper, I think it's David Gossett et al. Put out, where they were advocating a similar approach, where they said if you have some shallow circuit already that you can use for QAOA, then just do one iteration of an algorithm that's of a similar spirit to ours, and you can improve the energy by a certain amount, reduce the energy by a certain amount. And if your initial guess state is pretty shallow, the circuit depths required to run this thing are not too bad. So you're not getting to the ground state, but you have this guaranteed cooling anyway that could be useful. So that's one approach you can take. Just forget about the ground state, but just have something a bit closer. Um, or maybe you can throw away guarantees. Maybe you can forget about using the step size that we have derived has guarantees, and instead use a much bigger step size and see how you do. Um, but we were not really in this paper thinking about now. We were
Right. Okay.
maybe about early fault tolerant, maybe fault tolerant, and that's an interesting future step to try and really understand to what extent it can be
Yeah.
made.
Of course. Of course. Yeah. So, I mean, there's sort of two aspects to this. One, as you said, is sort of the thought experiment of what can you do once you have a fault tolerant machine, and then there's the trade offs that can make it potentially runnable on existing machines. Do you think those trade offs could lead to sort of scientific value? I mean, what's interesting to me is that the devices that we're building now are starting to produce sort of novel scientific results for physical sciences. In other words, simulation of quantum systems. Utility, I think, is the term that IBM uses, but it's really in a scientific setting rather than trying to figure out sort of the theoretical field of quantum information. And once we have fault tolerant machines at scale, it's like, what can we do scientifically that's useful with the machines we have today? Is that sort of one of your areas of focus?
I mean, so I completely, I mean, yes, I think current machines are most likely to be useful for many body physics problems, maybe quantum chemistry problems. Um, I think they probably haven't been useful yet, and I think most people would agree with that, that they've not. They are becoming interesting to benchmark different methods, to compare classical simulations to quantum simulation methods. I think it's now challenging to simulate some of these devices, and that makes it a fun tool to help develop our methods for simulating quantum systems, things along those lines. Um, I think in the near future, yes, applications are most likely to be within the physical sciences. Um, but you seem to present a dichotomy, sort of, is it just useful for the physical sciences or is it useful for the rest of the world? But I'd say that things that are useful for the physical sciences are
True.
also useful for the rest of the world.
True.
So
True. Yes. That's an arbitrary categorization that somewhat maps to the way industry sees it, right? I mean, the analogy I use often is Monte Carlo classical was created by Stan Ulam and others at Princeton Institute for Advanced Studies for I think it was proton diffusion calculations initially, but it was is a physical science application initially, and then that was like 1950 something or 40 something, and then 1977 is the first application of Monte Carlo in a financial services setting. And so to a certain degree, it's that kind of map that the overall quantum computing industry is looking for. It's like techniques emerging from physical sciences applications and scientific applications of the devices we have today, leading almost serendipitously to broader application with more direct, sort of economic impact rather than scientific impact.
Even you took it as far as financial forecasting or whatever, then I don't think you need to take it as far as financial forecasting in order for it to have an impact on society. If you have a better understanding of catalysts for chemical reactions, I'm not a chemist, but that's going to be useful for all of these different companies.
Yeah, and I mean the speculation about the earliest use cases tend to be sort of battery technology or FOMOCO or right. I mean, these are the scenarios, and I agree. I mean, I use the Monte Carlo and the financial service just because it's sort of that's on the it's the most obvious sort of dichotomy between scientific technique and then broadly applicable general algorithm. But yeah, I mean, so when you think about those types of early use cases, do you think that's still something that's going to require fault tolerance to actually deliver those scientific applications, scientific uses, and scientific value, or do you think there's value in this NISQ era or like late NISQ era, early fault tolerance era?
That's a big question.
Hmm.
And I think, again, it depends what you mean by scientific value. I think if you mean scientific value for studying problems that are interesting to physicists, understanding better the dynamics of all sorts of different spin chains that can help us model all sorts of different magnetic materials, I think there's value there. Um, if you are talking about an application that will bring commercial value with a scientific topic, I think it remains to be seen. Um, I think there are maybe there's a growing body of research into approaches that are very, very, very lightly quantum assisted. So the algorithm is almost entirely classical, usually non-variational now, though some of them have a variational component, with just using the quantum for a minor subroutine. And maybe using the quantum system for that minor subroutine brings some kind of heuristic advantage. Probably not a provable one, probably not an exponential one, maybe one where then someone a couple of years later classically figures out a way of doing it. Um, that said, the other thing that I think is important to highlight here, I'm a strong believer that there is at this moment this sort of dichotomy, this competition between classical and quantum methods. But in this competition between classical and quantum methods, we are improving our strategies to understand systems, to model these systems. If the sort of scientists are competitive shits, and if the main benefit of quantum computing is it triggers that competitive shitness in us and gets us to come up with better classical methods that help us solve problems. I mean, it's an expensive way of doing it, but it's still a good thing. And I think we are going to increasingly see that hopefully small quantum subroutines maybe have some form of added benefit, even if not full scalable benefit.
Yeah, and there's also, I mean, another aspect of that sort of dichotomy that may be not valid is sort of the whatever. There's value in NISQ and variational techniques using NISQ machines versus there is no value and we have to wait for fault tolerance. It seems like you're much more um, open to the possibility of there being more value from this kind of phase of the machines that we have today, right?
I'm a scientist. I'm not a business person. I don't have to put my where my mouth is. I it's a fun challenge.
Yeah. And to be clear, I mean value in the broadest sense. I'm not meaning dollars and cents value. I mean, as you say, if it progresses information science, that's fantastic. If it progresses quantum mechanics and our understanding of the quantum world, that was fantastic. There's, it's more, I guess is it fertile territory for those types of discoveries that drive our knowledge ahead? Not, I guess what I'm saying is distinct from driving quantum technology itself, but like deriving knowledge from the use of the technology we can make today, if that makes sense.
So yeah, I am still optimistic in
Yes.
physics settings.
Yes. Okay. Okay. And one of the arguments you've already mentioned is against that is that it's just heuristics, and therefore there isn't sort of a theoretical basis to provably derive advantage. But that's sort of beside the point from your perspective. Is that right? I mean, if a heuristic works, the heuristic works. It doesn't really matter.
I'm not. I mean, we do have all sorts of provable advantages in different settings. What I was talking about is provable advantage for algorithms that we think are going to have an advantage in a near-term setting,
Okay.
particularly for applications that are of broader interest. I think we don't have that yet.
Right. Right.
But I think we have a number of different groups putting forward different approaches where they maybe have guarantees for their approaches, they maybe don't. But maybe the classical case doesn't have guarantees either. And so it's just a game of who can do best at that moment in time.
Right. Right. Yeah, and the evolution of classical algorithms often starts with heuristics and just whatever's pragmatically working at the time, and then after the fact, there's some sort of theoretical proof or foundation laid down to codify it. So I think it's entirely reasonable to expect the same in quantum computing. So if you're you were part of that review paper, which was sort of looking at the myths of no-go theorems, or what we can expect and can't expect from NISQ machines. Given your overall sort of more optimistic stance, what do you think you'll be focused on in the coming year or two in terms of research areas?
So one area of research I really like is trying to understand the scalability of variational methods in quantum computing. That's historically something I've worked on a lot, and I somewhat feel we're reaching a dead end with it, but it's still a question that I find very theoretically interesting, because the point is we have these quantum algorithms that have guarantees, but these variational ones don't. And we can prove lots of no-goes against them scaling in certain regimes. And so actually over the last 5 years, me and a bunch of others have collected a sort of big set of seemingly damning evidence about these scaling. And yet you have to concede, and we do this in the paper on myths, our perspective on myths, that these no-goes don't absolutely rule out anything. We're trying to stare into a crystal ball. We have arguments why in certain cases these things are unlikely to scale, but we have to allow the possibility that heuristically things could work out better in certain. That said, heuristically things working out better in certain cases, there are heuristics and heuristics. I think if you just slap some kind of completely, I mean, it does work sometimes classically, but I guess I want to know why a quantum method is going to be better. And I think sometimes a mistake people have maybe made is they take a problem that doesn't seem to be inherently quantum at all, and the quantum solution will be better. I am more optimistic when it comes to, at least in the nearish term, quantum problems being tackled on quantum devices, where we can make use of the structure of those quantum problems to do something more interesting. So particularly in a variational context. And so that's why I started looking at these cooling-based algorithms, because it seems to be more natural to take inspiration, have an inductive bias based around something that should work, and modify that, rather than sort of searching in these exponentially large spaces kind of blindly.
Yeah. And when you think about the quantum imaginary time evolution, the ability to implement that in some kind of useful way, do you think that'll be affected more by things like the new generation of superconducting devices, for example, that are either cat qubits or dual rail qubits that are better at identifying or suppressing certain types of errors. So in other words, do you think increased fidelity of superconducting devices is going to help, or increasing scale of high fidelity devices like trapped ions or neutral atoms?
I mean, higher fidelity is better. Well, high fidelity proportional to other factors like the time it takes to implement the gates and things along those lines, the decoherence times. But in general, yes, of course, we need.
Well, I guess what I'm saying is, if you think of superconducting as fast but noisy, and atom based as higher fidelity but slower, are you going to, or do you expect greater gains from your perspective from increasing fidelity on fast gate devices like superconducting, or increasing scale on slower atom based devices?
It depends which hat I've got on, but for this sort of this new line of research in terms of these non-variational cooling algorithms, they don't need to be fast. So just give me high fidelity gates. That's what I want. Uh, in terms of um, dynamical simulation, um, well, we want high fidelity and we want big to try and make it beyond what can be done classically. And we want a good topology. So you're going to be balancing all those components out. Um, in terms of variational stuff, I don't think, well, correct me if I'm wrong, but no one seems to be that optimistic about implementing large variational algorithms on current hardware, pushing beyond what we can do classically. I feel like the combination of hardware noise, bound plateaus, local minima, uh, expressivity limitation, lacks of good ansatzer, all of those, I think, makes people relatively pessimistic for right now. But there are people who are optimistic for soon. I'm not sure how optimistic I am for soon, but there are some people who are more optimistic for soon.
Yeah, I mean, I think the only exception to what you're saying, I think, would be the generative quantum eigensolver work that Alan Asper-Guzik and others are doing, where they're trying to bring accelerated classical computing and machine learning to improve the ansatz, and therefore reduce the sort of, yeah, I mean, it's,
I don't think that avoids any of the problems. I think it's no worse, but no better than the issues that all of the other approaches face. In my take. But there are different opinions on how much these issues are issues. Um, but I think the point is, so with the variational approaches, you need both them to be quick and noise to be relatively low, and we don't have that. Because the combination of the noise and the landscape being flat is really, really damning right now.
yeah, and I mean, I guess the fidelity in superconducting is promising to increase, but that's sort of resetting the scale in a sense, right? I mean, you've got quantum circuits incorporated dual rail qubit device is going to be 8 qubits. IBM's LDPC logical qubit device, that chip is 288 physical qubits. It's going to be 12 logical qubits according to their research papers. So in other words, there is increased fidelity coming down the pipe, but it's decreasing the scale of the system that you can actually simulate.
Yeah, or some of the atomic ion devices, trapped ion, Rydberg atoms, they have higher fidelities. So
Rydberg atoms don't have gates yet, so that's a bit of an issue. But yeah, the trapped ion devices. I mean, Quantinuum's got a roadmap to get a large number of qubits shipped in the near future as well. So there's always hope for the next device.
even, I mean, Quantinuum's got, is it 54 or 56, something like
Yeah,
that?
56. Yeah,
I mean, that's enough to be challenging someone's laptop, enough to
that's
be
definitely true. Yeah,
enough to be challenging actually someone on a cluster too, if you're doing something
yeah,
interesting.
that's true.
But yeah, you're not going to be doing variation on that for what that's worth.
Right. Is that a scale that potentially QITE would be implement in some one of those, like you said, the bigger time step kind of scale?
Yeah, potentially. We've talked a bit about that and just need to think about a good application.
That'd be really interesting. So I guess if you look ahead again, do you think you'll continue more to progress this idea to try to get to that implementation on running on real hardware, or do you think you'll continue on more down the theory track?
We are exploring all branches there currently. So we're exploring all sorts of sort of long-term theoretical understandings of the algorithm and how it can be applied. We're exploring different applications of it. We're exploring different variants of it. We also are interested in nearer term, more heuristic variants. I should say that in parallel, so you asked about my research earlier. So this is one avenue. Then sort of variational stuff, is it screwed or is it not, is another area. The final one I have is I also have one foot in sort of the classical simulation pool. So almost the other side of the barrier. So I think actually only by understanding the limits of your classical simulation methods, not only are you going to be able to figure out when you can get advantage, but also figure out how best to use these devices. So been developing what we call these Pauli propagation algorithms, and we have all sorts of ideas about how to try and not just use them on their own as a competitor, though we do like using them on a competitor, but also combine them with in order to get the most. Because that then goes back also to the point I was saying before, that if we're going to make the most of these devices in the near term, I suspect it may well be for just some tiny subroutine with a lot of the rest of the work done.
And what's an example of that? I mean, hypothetically, what would an example of that sort of classical plus quantum solution look like versus a variational, which is sort of, that's also hybrid, but it's iterating back and forth between the classical and the quantum?
Yeah, different. I'll give you two examples. So one, I've got some students who have worked on things like using tensor networks to try and compile some really short depth circuits. Would use tensor networks to simulate as long as you can classically, then compress that down into a short depth circuit. Then you could apply that circuit on hardware, and actually you'd use that circuit on hardware just to do some Schrodinger evolution, some like evolution of state. But you can also back evolve the observable, and that bit can be done classically. So you're going to have these sort of classical methods pinning in from both angles and just a little bit of. So that's one example, and then you've got all sorts of people trying to explore variants where you get samples from your quantum computer, and those samples maybe are used to project down into a subspace for diagonalizing Hamiltonian. So IBM have been really pushing these methods, and they have some nice guarantees for them in certain settings. But then the big question there is, are you actually adding anything that you couldn't do classically? So they completely see that this is an algorithm that is practical on common devices. You are getting this little bit of quantum added value, but the question is it actually enough added value that you can do it classically? But interesting direction. And then there are other approaches people are considering that are using sampling. You may be trained classically, do some kind of training classically, for example in generative modeling, and then you get samples from your algorithm. That you might have an algorithm that's the classical bit might be hard to sample from, but if you can train classically to get some circuit and then sample on the hardware, you get added advantage from the hardware of producing these samples. So things along those lines.
That's really cool. That's excellent. Well, thank you very much, Zoe. This has been fascinating. I'm going to continue to watch the work from your group and from EPFL generally, and at some point we may have you back on for an update as you progress your work. But thank you very much.
Cool. Thanks for having me.
The podcast is a production of the New Quantum Era, hosted by me, Sebastian Hassinger, produced by Ian McGuire, with music by Omar Costa Hamido. If you have feedback, you can respond directly to the post on Blue Sky for this episode, or leave a review or feedback on whatever site you get your podcasts on. Or you can go to newquantumera.com and have access to the website for the podcast as well as for the book I'm writing for O'Reilly Media. Thanks, and we'll see you next time.